So my talk is about groups and the fast and flexible decision-making that's needed for them to be successful when they manage the uncertainty, the variability, the dynamic change that they experience when functioning in the real world. And I'll make precise what I mean by fast and flexible. And I'm also going to explain to you how we arrive at these notions of what we call tunable and selective sensitivity to distributed stimuli over a group that can help us understand how groups can balance the ability to be responsive but also robust in these complex environments. So the work that I'm going to talk about today builds on a history of prior work, and it's also closely related to several well-established literatures, including there's a big literature on consensus dynamics, but it also builds on models and results in computational neuroscience for decision-making, and also in this world of collective animal behavior. My colleagues in this work include Anastasia Bizyaeva, who's a former PhD student, and Alessio Franchi, who's a longtime collaborator. So I've been studying collective animal behavior for almost 25 years, and I never get tired of this video. It's so beautiful. This is a video taken by colleagues in Rome of more than 1,000 starlings. They're actually over the train station, and they're moving together in the presence of a falcon. There's no leader in the group, and yet the birds, as you can see, they move so quickly and in some kind of unified way, and they somehow seem to be impervious to what must be a lot of uncertainty and all sorts of fluctuations. Moreover, these displays, these remarkable displays of animals in the wild, they don't always depend on a solution that leads them to a consensus. They're not always trying to agree. Sometimes they have to disagree. So this is a little example where you see that every fish has decided to go in almost every possible direction, and yet it's somehow this very nicely coordinated kind of display. A critical feature of group decision-making is breaking what we call indecision. So this is the way in which groups can avoid deadlock or collision, which can be super costly, especially for animal groups. So I'm illustrating this with this group of these 5 wheeled robots, and they're just programmed with simple dynamics that just direct them to move across the room. And so on the left, they didn't know what to do. They come to this deadlock so they don't actually crash. So this problem of how to break indecision, especially if there's no evidence for one option being better than another, for example, whether to pass left or right, is actually a big open problem. And understanding how animals do it, understanding what the mechanisms might be. And this is one of the issues that we address in the framework that I'm going to talk about today. So I'm going to illustrate these dynamics. They're programmed into these robots, so now they're using the dynamics I'm going to show you today so that they make a decision collectively to pass either left or right without, again, any evidence that one is going to be better than the other. So I've studied a bunch of different collective behaviors in a variety of model organisms. And I'm going to just tell you about a few of those, the ones that have been particularly inspiring for this work that my collaborators and I have done to develop an understanding of what makes for fast and flexible group decision-making. So the first I'm showing you here, actually the plot on the right is from this paper by Ian Cousin and his colleagues. And it shows the results of it's actually a simulation study of animals moving on a planar surface together. And much actually like this, these are golden shiners. So this is a fish school moving in a very shallow freshwater tank. And in this setting, there are 2 subgroups, and they're equal-sized subgroups. So one subgroup is trained to prefer or to know about one of these target directions, like the yellow target. The other is trained to know about the blue target direction. So you put them in the tank or you run the simulation, and what happens is the group doesn't want to split. So they stick together, and when they're sort of far away and those targets are somewhat indistinguishable, they kind of head down in the average direction. And then when they get close enough so that the angle between them is above some critical value, what you see on the right, and what happens in the experiment is that they actually very quickly, with equal probability, go either left or right. This is a heat map showing you the frequency of the different group directions as a function of this angle as it's growing, as they're moving closer to the targets. So one thing to note is this very fast jump here. I mean, this is very nonlinear. It's almost like a switch at this critical value. A second group that I've studied that has been also incredibly inspirational is these questions around nest site selection by a swarm of honeybees. So this problem is kind of incredible. I mean, it's very well known how these honeybees make a choice as a swarm when they're confronted with a whole bunch of candidate nest sites. They're able to pick the best in terms of what they understand or what we know they understand to be the quality, the value of these sites. And they do that using a whole bunch of mechanisms, but one I'm showing you in the top right figure, which is the way that they communicate and advertise. It's called the waggle dance. So on the vertical surface of a swarm, a bee who has scouted out and been committed to a particular site comes back and does a dance. They're vibrating their abdomen in a sort of figure 8 pattern, and the angle of the sort of the straight part of the figure 8 relative to the vertical tells the observing bees the direction relative to the sun of the site where this candidate nest site is, and the number of waggles tells them how far it is, and also the sort of the excitement, the speed at which they do this, and the number of these figure 8s tells them the quality. So this is already kind of incredible. But there was, at a certain point, it was discovered that they do something else. There's another signal that they use. It's called a stop signal. So this is when a bee who's watching a dance will actually headbutt the dancer bee. And so Tom Seeley and his colleagues did an experiment and wrote this paper that appeared in Science in 2011 to try to sort of understand what was going on. And what they did in this experiment was that they presented the honeybees with 2 nest sites of equal value or near equal value. And what they did was observe that this stop signal was actually what you would call a cross-inhibitory signal. So those who had committed to site A would headbutt those who were dancing for site B and vice versa. And so they derived a mean field model, a well-mixed model, to try to understand something about what this stop signaling role might be in this process of making a decision. Because what they saw the bees do very reliably was to actually essentially flip a coin and pick one of these 2 equal value nest sites, which is kind of incredible. I mean, like they didn't wait and negotiate and, oh, should I go this way? This way, they just do it, and they do it very efficiently. And so what they essentially saw with this model was that, so here sigma is meant to represent the rate at which they're doing this stop signaling. So when it was low, what you're looking at on the top left is, on the triangular plot, psi sub A is the fraction of the bees that are committed to option A and or candidate nest site A, and psi B is the fraction for nest site B. And what you're seeing is that when the rate of stop signaling is too low, they converge on the black dot, which is essentially an indecision, a deadlock. They can't choose. When the stop signaling rate is large enough, that becomes, the open circle becomes an unstable solution, and in the model you see that, we have this bistability, everybody for A or everybody for B. And so I got very interested in this, and with some of the co-authors of that paper and my student Darren Pice, we we basically set out to analyze this and try to understand this mechanism and how it all worked. And I'm showing you a plot from our paper, in which again, so I'm plotting now this sort of the fraction. So at the top of the vertical axis is everybody's for A, at the bottom everybody's for B. In the center, when it's right at the 0, that's the deadlock. I'm plotting that as a function of this stop signaling rate. And so what happens is that we find that there's actually this critical value. When the stop signaling rate is below it, the only solution is just this deadlock. When the stop signaling rate is above it, that becomes unstable. That's what the red line is meant to indicate. And these two solutions for everybody for A, or majority for A, majority for B, they actually make a decision based on a quorum, so they only need a majority. Those become the solutions, the stable solutions, with equal probability. And furthermore, what we were able to show is that the critical value actually depends upon the value, the average value, the quality of these equal or near equal nest sites, which is kind of also incredible, because it says if the bees have, say, evolved to do stop signaling at a certain rate, then if the sites, the candidate nest sites, are really good, then this critical value will be way over to the left, so quickly they'll make a decision. If they're actually really poor, then that critical value will be way over to the right, and they'll be stuck in a decision, which makes sense, that they should wait for another option to come along. I've also been inspired. This is some data that we collected for this paper that we wrote with Deborah Gordon, who's a biologist at Stanford, and she studies these desert harvester ants in the desert of Arizona. So here she's asking questions that she wanted us to help her with, which had to do with the regulation of their foraging. So these ants go out and they collect seeds. They don't leave pheromone trails. These seeds are blown by wind and water, and so it doesn't make sense to leave a trail. But they make decisions about whether to go out, and they have to be really, really careful, because on hot and dry days, if they go out, they'll lose more water than they could metabolize from the seeds. So she's interested in understanding, how they're able to be so, some of the colonies are able to do this regulation of foraging in a way that's incredibly sort of resilient and responsive to changing temperature and humidity on the order of minutes or hours. And so we set out to study that, and this whole idea of this ability of these groups with like incredibly little information as individuals, and even very little contact with one another, communication with one another, to be able to not only regulate their foraging and adapt or modify in response to the environment is something that I find really a fascinating and compelling question. A project that I have now, this is a sort of a new problem, and I think it's, we're basically about to set the tools that I'm going to show you today on this problem, has to do with this problem of understanding how cascades among fish who should be foraging and should only cascade away in an escape response when there's a real threat, are able to like with high probability, avoid a false alarm, avoid cascading away from their foraging when somebody does one of these escape maneuvers spuriously. So this is a really beautiful problem, and one that we're going to address with these questions, with these tools. So with that as sort of a setup, let me then tell you that we define fast as the ability of a group to break indecision, but just as quickly as indecision becomes costly. Right? So it's not about just making quick decisions when you don't need to. It's about making quick decisions when you need to. And this requires not just that you're going to be attracted to something else, but also that you're going to be driven quickly away from something that you don't want to do, indecision, right? You don't want to be stuck here. So it's not just that, you see that there's something else to do. It's that it's no longer a stable solution, and you're going to get out of there fast. You're going to get out of the way. By flexible, what I mean is that this ability to adapt to signals that are important to the successful functioning, even if they're weak and rare. So we want to be able to understand how these groups are able to respond to the real signals and then somehow reject unimportant fluctuations, so without compromising their robustness. So this is where this notion of what we call tunable sensitivity to inputs come in. This idea that you don't necessarily have to pay the cost, like those fish on the coral reefs that was in French Polynesia, don't necessarily have to make themselves so sensitive to everything, because if they're not sensitive enough, they get eaten. But if they're so sensitive, then they're never going to get fed because they're going to be responding all the time. So tunable sensitivity means that there should be some very simple way in which a system can modulate its parameters. So there are some regimes in which you're going to be sensitive and some regimes in which you're going to be robust. And this is what we're after. And sort of the net sum is that these are very much nonlinear kinds of phenomena. They're very much connected to this whole notion of feedback, which I'll describe to you. So dynamics that are nonlinear, that have feedback, and for me it's very important to try to understand this with tools that give us analytic tractability. So I don't want to just show you simulations, I want to show you how we can get in and understand so that we can come up with hypotheses, testable hypotheses and things like that. So we set up a sort of modeling framework where we think about N sub A agents. So each individual, or it could be a subpopulation, is represented by one of these circles, and we have N sub A of them. And then we imagine, so we're going to really think about systems or these groups where there's some kind of either communication or ability to sense at least some of the others in the group. And those are represented by the lines connecting the dots, or the circles, so they're red or blue. Blue means that the sign is positive. So that means if I have a blue arrow to David, if it's a sensing arrow, it means that I can observe what sort of what he's doing, and I will kind of follow suit. Whereas if it's red, I'll kind of do the opposite thing. So that could simply mean that we're coming to an obstacle, and he's going to go right. If you're going to go right, I'm going to go left, kind of thing. So because there's not room for both of us on one side, and they can be one-way arrows. So maybe I'm sensing David, but he can't see me because he's facing the other way, something like that. So these little AIKs. So we think about a matrix with the ikth element representing the weight that the agent I puts on the information that it's getting from agent J. K, sorry. We also can have a network among options or strategies or beliefs, whichever these are. And so the same idea. So if we have J's and L's representing our options, then we could have this kind of network. So for example, if you have two mutually exclusive options, like whether to go right or whether to go left, or I can't move to both candidate nest sites, so one or the other, then I would have a negative sign, because if I'm for one, then I'm not going to be for the other. But if there are two targets and I can't distinguish them, then if I'm for one, I'm for the other. That's how we understand that I would go straight down the middle. So our starting point is then to think about this decision-making process for this network system as a dynamical, continuous time process. So this evolution over time of agents' decision states, and we're going to define one of these sets of states as, we're going to call them opinions. Okay, so that's just our word for it. So Zij at time t is just a real number, and it's the opinion that agent I has about option J at time t. Okay, so the more positive it is, the more in favor agent I is of option J, the more negative, the more in disfavor. When it's zero, that's when it's neutral or undecided or at a deadlock about option J. Then we also are going to assign to each agent this notion of attention. So attention, so that's again a name we give to it, so you can interpret it. In fact, it's going to play a very similar role to the stop signaling rate. So it's essentially like a multiplicative factor, a gain on, like a dial on how much I'm paying attention to what what David's doing. And we want to think about that as a variable. In fact, it's going to be very important to this whole notion of tunability. So how do animals, and then how does the group as a whole make decisions because their attention is changing? If I see some people in the back stand up, I'm not going to start deciding whether to go out that door or that door, but I might start suspecting maybe you smell smoke and there's a fire, and so I'm going to get involved, or the election's coming, or the collision is coming, and I'm going to get involved in the decision-making process. So we even might have a network associated with that. It's sort of like which agents are going to influence my attention dynamics. So I'm going to think about Z as just the vector of each component is each of these agents' opinions. This vector of U is all the attention parameters. And so this sort of story is that this process is going to be, I'm going to explain this, organized by what we call bifurcations. It's going to be controlled by this notion of feedback, and it's going to be modulated by network structure. And we can kind of tell this whole story, and we can also tell this story even in the presence of uncertainty, because a lot of this, all of it sort of holds up even in the presence of noise and uncertainties. And that's pretty exciting. I want to say one other thing. I'm going to show you a model, and I want to make the point that the model is not just an ad hoc model. It certainly has built on models like from computational neuroscience, as I mentioned. But it also derives from what we call a model-independent approach. So this is work done with a couple of mathematicians, Marty Golubitsky and Ewan Stewart, where we think about so model-independent means that we're relying to make some predictions solely on some empirically verifiable assumptions. And those include that opinions evolve continuously in time, and that opinion formation is a network phenomenon. And we use mathematics to say something about these kind of ground truths, which allow us then to build a model. So a ground truth, for example, is that it shouldn't be, especially in a very symmetric setting, it shouldn't be hard. And we see it all the time. Think about a school of fish that might go this way or might split. It just shouldn't be hard, and it shouldn't require all kinds of fine-tuning for a group to be able to switch very quickly from a sort of a consensus decision to a dissensus decision. And so this kind of mathematics allows us to propose a model that actually captures these model-independent ground truths. And then we can take it from there. Then we can use the model itself to explore even more general and heterogeneous and messier contexts. Okay, so I'm going to give you the model. I'm going to step through this carefully. I mean, you just need to understand the sort of the basics principles, because the first equation, the dot just means that this is the update. This is the rate of change of agent I's opinion about option J. So it's just how it updates it. So I'm going to go through all the terms on the right. The first is just, if there's nothing else going on, this is just like a little damper. It just brings me back to neutral. There's no reason to make a decision. I'm just going to be regulating, to neutral. And that's a negative feedback. It's a regulatory kind of term. I can have my stimulus, so Bij here is the stimulus for agent I about option J. It could be positive, then it's something in favor of option J, negative, in disfavor. Then the middle term is a positive feedback. It's what's gonna make me change my opinion from the neutral. Okay, and the first term is a self-reinforcing term. So it's kind of a snowball effect. I get kind of, my opinion goes up, and I'm kind of like, oh yeah, this is a good idea, and I'm getting more involved. Then we have the term where I'm looking at my neighbors. So this is just a weighted sum with through the network of what I'm observing of whoever I can observe, and that's affecting my opinion, because I'm either doing what they're doing or I'm doing the opposite of what they're doing, depending upon the weights. Then there's also kind of the internal belief systems. So this is kind of adjusting to align my belief system network. So if I'm for something, I'm gonna make my opinion of J, if the edge weight is positive, also I'm gonna become more for that option. And then this is my reaction to others' opinions about other options, which has this sort of multiplicative effect. And in front of all of that is where I put this dial, this attention. So I'm going to weight through this UI for each agent how much they're actually going to pay attention to all of that stuff. And this whole thing is a positive feedback. So this is the only place we actually introduce a nonlinearity, and this is very much built from biophysical models where you see these kind of saturation functions. So we're basically going to essentially if the signal coming in from my observations is small or intermediate, I'm going to treat it as it is. It's just if it gets so loud in favor, I'm going to cap it at 1. And if it gets so loud in disfavor, I'm going to cap it at -1. Then I have my update of my attention, and it could be at a different time scale. That's the tau u. I have some kind of basal attention level, u naught. And then I have this feedback gain, k sub u. So when k sub u is not 0, I have this additional feedback. This is like what I was talking about. If even if there's like a little bit of input and my opinion goes up, or I sense somebody's opinion going up, that's going to drive my attention to go up, and it's going to snowball, right? Because if my attention goes up, then my dial goes up on the first equation, and then my opinion goes up, and other people's opinion or other agents' opinions might go up, and so we get this additional feedback. Okay, so that's the model, and now let me show you what a simulation looks like. So a simulation that illustrates how this coupled dynamical process yields this kind of fast indecision breaking with an implicit threshold that we're going to completely try to understand, and we're going to understand how it's tunable. But this is a threshold on these distributed inputs. So what makes for something that's going to make the system respond, and what makes for something that's going to make the system be robust and not respond. So what you're looking at is a network of 13 agents. Okay, and the gray lines are showing, who's connected to who. All the edges on top. This is actually the same structure. That all the edges on top have a weight of +1. All the edges in the bottom have a weight of -1. That's the only difference. I'll explain later what the size of the circles are. The size of the circles actually are going to be what we can actually compute as the sensitivity of that individual based on where they are in the network to the stimulus that's coming their way. So in this simulation, there are going to be 2 mutually exclusive options. So I can plot ZI1. That's every agent I's opinion about option 1, because if it's positive, they're for 1. If it's negative, they're for option 2, because they're mutually exclusive. And what I'm going to do is give an input to 4 agents, 3, 6, 10, and 11. And I'm going to give agents 6 and 10, I'm going to give an input of the same magnitude B, and 2 of them, the ones in blue, are going to get it in favor of option 1, positive, and 2 are going to get it negative in favor of option 2. And I'm going to apply it for just a short period of time. I'm going to turn it on, and then I'm going to turn it off, as you see over here. And I'm going to do, on the left, these 2 plots, in the middle, I'm going to give them a little bit, 0.1, and on the right, they're going to be 0.3. And this is what happens. Okay, I've added, so I'm using hyperbolic tangent. I've added a whole bunch of uncertainty on every single parameter. I've added some noise. And this is what happens. So clearly, on the left, we're not getting anything really much, right? The ones that are getting inputs go up and then they go down. And nothing much happens. On the right, we're getting this huge cascade. Top, it's for option 1, and one reason to know that, or you could predict that it's for option 1, is that 6 and 10 are bigger size circles. They're more sensitive to the input. And what's also interesting about the bottom is so they split, and that's kind of interesting because it's homogeneous. That all the edges are -1, and yet there's splitting based on the network structure. Of some go for option 1 and some go for option 2. And there's a whole bunch of interesting things happening. So there's certainly the robustness to all that uncertainty and noise. But there's also, because of this nonlinearity, first of all, you can see this things happen very fast, almost switch-like. So one of the stories in this is that we start with a continuous time process, and we see things that look very discrete. discrete in time. So like when you think about a school of fish and you see this, it can come from something that's continuous in time. So we get these, because of the nonlinearity too, look, we get the magnitude of the opinion when it forms is much larger than the input. It also persists, so we have multi-stability, so it persists. It's a new solution that's stable, even if we turn off the input, the stimulus. Also, individuals that are given, they don't always go in the ones who are given some stimulus, they don't always end up going in that direction. That's because of the network, right? They're being pulled. There's enough pull from others that everybody's making a choice for option one, even though two of them were given stimulus for something else. So what's happening and the way we can explain it is through what we call an indecision-breaking bifurcation. So for those of you who aren't familiar, formally in mathematics, a local bifurcation simply refers to a change as a function of a parameter that we call a bifurcation parameter in the number of steady-state solutions and their stability. And/or their stability. And so what I'm plotting you here is what's called a bifurcation diagram. So it's merely a picture, a plot. So this Y here, think about it as like a lumped opinion for the network. And I'm plotting that as a function of like an average attention for the network. And so when Y is equal to 0, that's our indecision. And there's some kind of critical value of attention such that when, here the solid lines are stable and the dashed line are unstable. So for all these different values of attention, we have only indecision that's the only solution. So all the, I can sort of show you for initial conditions here, everything's just converging into indecision, right? I don't have enough attention. You can think about that equation. I had the negative feedback, which is regulating me there. When U is too small, it's dominating. But when U gets really large, I get a decision, right? I get this formation of an opinion because indecision becomes unstable, and these I call them decision state 1 and decision state 2 become stable. And here everything's symmetric because I haven't introduced any kind of stimulus. So stimulus here, the sort of distributed stimulus is this B. So this is indecision breaking, but we get this, what we call ultrasensitivity, because when we add, and again, we know how to, we understand this formally very fundamentally and very systematically, that even the tiniest bit of input, we're essentially talking about a point that's a singularity in our system. So any little bit of input's going to give us a big response. So this is called an unfolding of this picture. So it looks kind of the same on both ends, but in the center it looks very different. So a little bit of positive input means that the decision state 1 is always a solution, and it takes a lot of attention and certain initial conditions to get the other solution to happen. So same initial conditions as before. Now when U is small, we go a little ways, but when U is a little bit bigger across this critical value, we can get these big solutions. So this is ultrasensitivity to stimulus or input. And I want to just illustrate this again with a different robot, but so here's avoiding deadlock and collision through indecision breaking. So two mutually exclusive options. Basically, we're putting these dynamics on this little robot, either to go right or to go left. Indecision would be going straight. It's trying to get to behind where that person is standing, but its attention is going to grow as it senses that there's an impending, because it can measure the heading direction of this person and the relative position. So it's going to increase its attention, and then we're using that to drive how it turns itself, how it steers itself. So here it goes. It has no bias in this case, and so sort of just essentially noise. It's kind of, sometimes it might measure the person going a little bit to the right or a little left, and so, with equal probability, it would either go to the right or the left. here's a case where we give it a tiny little bias. Okay, it's in the US, so maybe it should think about going to the right, but okay, the person's maybe from the UK and went to their left. And but it has this ultra sensitivity, so it starts, you can see it's starting to go to its right, and then it very quickly recovers, and it can change its mind because it's so super sensitive. So what we do for the big network is prove what we call this indecision breaking bifurcation, and we're able to understand this notion of a critical subspace. So for those of you who are familiar with linearizing dynamical system, we have this high-dimensional system. We can linearize it. We can find the eigenvalues with the zero real part. The bifurcation happens along that. It's called the center manifold, which is tangent to this, what we call the critical subspace. And we can compute this. And the critical subspace is where everything happens. So some low-dimensional space is where this decision-making is happening. There's also a sensitivity subspace that we can compute. And that's if the inputs lie along that subspace, or if there's some component of input along that subspace, then we're going to trigger this, decision-making bifurcation, decision-breaking bifurcation. In the case of these dynamics, we can prove conditions under which you just get these zero eigenvalues. So the critical subspace is just one-dimensional. It's just this vector. And the components in it tell us the relative strength of preference when these form opinions. And the sensitivity space is just as one vector, and those components of W are the sizes of the circles that I showed you, the sensitivity. So Y is just the projection of these opinions onto this critical subspace, and B is the projection of the vector of these inputs coming in distributed across the network onto this sensitivity subspace. And so that's why we call it selective ultrasensitivity, because if the input, it could be very small, and aligned, it will pass, and it will maybe lead to something. If it's transverse or orthogonal, it could be very large, and we won't see anything. So it could very well be that just changes in like those edge weights and strengths could be moving this around so that certain signals are getting rejected and certain signals are being passed. So one of the punchlines is that we can compute all these things just knowing the network structure, which is really kind of exciting. So I think it's easiest to see by example. So here's an example of just two agents with the positive edge between them. We can compute what the V actually looks like this. So now you're looking down remember the bifurcation? It looks like a pitchfork. It's called a pitchfork bifurcation. Now you're looking like the tines are poking into your face. And the center one is unstable. That's the indecision. And this is decision state one. So what we can compute is that it's along this direction. So this is agent 2's opinion of option 1, agent 1's opinion of option 1. They're both positive here, both for. Here they're both negative. They're both for option 2. In the case where this is a negative sign between them, this is the whole story just switches. This is the line in this high dimensional, I'm showing in a low dimensional setting. But now decision state 1 is agent 1 for option 1 and agent 2 for option 2. This is agent 1 for option 2 and agent 2 for option 1. And this generalizes. So if I have a whole bunch, we were looking at pictures of what this lumped state was doing, but this is what this analysis of the network structure tells us. Who's going to be the strongest in favor? If they go for option 1, it'll be the strongest in favor if they go for option 2. And likewise, if they split, if we have mixed signs in this V, some will go for, we can predict who goes for option A and or option 1, who goes for option 2. We can likewise do this when we have multiple options. So we can determine not only how agents distribute over options, but how an individual agent. This is how an individual distributes over its options, right? Am I for some and I'm disfavoring others? We can also understand conditions under which you won't just get a stable opinion, but you'll get an oscillation, steady oscillation, a sustained oscillation, right? And so we can show, for example, very systematically as a function of this is a belief system network with different interagent networks, and so we can say very systematically how the role of these interconnections affects the relative amplitudes, the relative phases, and the frequency of these oscillations, which is also super useful. Okay, so what I've showed you so far is the dynamics of the Z's, and I haven't yet introduced the other piece that makes this really fast, because that pitchfork bifurcation is kind of going to happen only as fast as attention is increasing. But if I make attention a variable, like I showed you in that second equation, then I get this additional positive feedback. Remember, attention is growing because opinion's growing, and then opinion's growing because attention's growing. And this is what gives us the switch-like behaviors, because the bifurcation diagram that I showed you before looks like this. Now, basal attention is our parameter, bifurcation parameter, but the direction of this pitchfork switches. So now in this, for these values, when the basal attention is actually below this critical value, I get this sort of tri-stability of the two decision states and indecision. And this gives me super interesting result, which is that with a tiny bit of B, well, depending upon the value of U naught, I don't gradually make a decision, I jump. This is my switch. So this is a hysteresis, right? Kind of like dum-de-dum-de-dum. If U naught is growing, then boom, I just make a switch. And so this hysteresis comes from the multi-stability. I mean, another way to look at it is to plot the lumped opinion state as a function of the stimulus, the distributed input, right? When the tension is really low, the basal attention is really low, we just get this kind of linear response. But as it grows, like in this blue region, we get this. We have two kinds of hysteresis here between decision state 1 and the neutral solution, and decision state 2 in the neutral solution. So, I mean, one thing to remember is that this jump is a cascade, right? It's a cascade of everybody forming an opinion and forming large opinions, potentially large opinions. And so if you can remember back to the simulation at the beginning, so this is like some critical value that was between 0.1 and 0.3, right? 0.3, we got the cascade. 0.1, we were just sticking around neutral. And so, I mean, hysteresis is great. If it gives me this robustness, right? I'm not going to switch with just small fluctuations in B once I've made a decision. It gives me memory, so convergence depends on past information. And importantly in our story is that this sort of the size of the hysteresis depends upon this basal attention. So it's just a simple parameter that modulates. So an animal group might be modulating that in response to the context, right? It needs to be more switchy, it needs to be less switchy. It needs to be more sensitive, it needs to be less sensitive. This is this idea of tunable sensitivity that we're looking for. I mean, here's just a little example of this robot now having to make a sequence of decisions and use this kind of sensitivity to move around in all different kinds of scenarios. And you can see now I'm plotting for you what the attention is doing in the orange at the bottom, and the opinion is doing in the green. So the final other takeaway is also this. I just want to come back once more to this notion of selective ultrasensitivity. So that whole story is, so it's not just becoming sensitive and not sensitive as U naught moves. That B is also a function of how the distributed input projects onto this sensitivity space. So I just wanted to make sure that that was a good, that this was well understood, this notion that even very small inputs can excite the dynamics along this critical subspace when they're aligned with this sensitivity subspace, and even large ones might not. because they might be misaligned. And you can think about, this notion of like whether you get a cascade or not, therefore depending not only on how big the input is, but how well aligned it is. And all of this is tunable by this basal attention, and it's modulated by the network structure, right, where this sensitivity subspace is. So we're bringing this back to this story of collective cascades. We want to understand this notion of, Andrew Hein is my collaborator on this. He's at Cornell, and he says, in the literature, it's always understood that it's sort of, this the cost that you pay. If you're a fish and you don't want to get eaten, then you've got to be more sensitive than you'd like, But what he says is that somehow that's not actually what seems to be the reality, that there does seem to be maybe this opportunity to understand that they're able to sort of modulate how they filter these signals, say by adjusting strengths of weights and things like that. So we're going to be doing some experiments. We're also trying to understand how to formulate the parameters in this model in terms of biology, what's understood about these. He's looking in this tank at zebrafish with an audible stimulus. And one last thing I just want to share with you because I'm excited about it. It's excitable decision making. So what I've told you is fast and flexible, right? This idea that you can make these fast decisions, right? But I haven't really told, like you could get stuck up there. It becomes actually very stable, right? And so, like, for example, in that little example of the illustration of the social navigator, here it's made a good decision, and it knows that it's got to move. It's this notion of like a sequential decision. Say it's moving around a person who pulled out their phone and now is drifting in front of them, has to actually go the other way. And it kind of realizes it's just too slow. Partly because, it's made this decision, and now the picture flips and it's got to make its way all the way down. But what if, instead of doing that, we let it make its decision and then immediately drive it back to that point of ultra sensitivity. So it's ready. It's ready again if it needs to make a decision up or to make a decision to go the other way. And that's really easy. It's taking the dynamics that we have and just adding another negative feedback, another kind of setting us back to the original indecision, but at a point in which we're ultra sensitive. So we can do that dynamically. And this is called excitable decision making. And so we can be ready to go the other direction. I just want to show you what that looks like. So this is very much built, of course, on the notion of spiking neurons. But here the idea is that we can understand that you could be spiking for going to the right or spiking for going to the left. And you can even see that the frequency is being regulated just very naturally to allow when you really need to when you really need to turn out of the way versus not. And this translates to network. So here's a hypothetical network of our fish and thinking about how we get these cascades as spikes in a group. Okay, I'll stop with that. Thank you for your attention. I want to thank my group, my family, and my funders. Thank you.